My name is Gustavo Espinosa, and this is Lab 2, Lines of Charge. Some of the key ideas that this lab will be touching on are the concept of a charge as a property of matter, the effect of this property in the real world, modeling the charge as a line, and using a computational model to model real-world systems. In this lab, we will be using our understanding of charge as a line in order to create a model of charge on common household objects. In this case, we will be using tape very similarly as we did in Lab 1. We will again float the tapes with each other. However, in this lab, instead of modeling our charge as a singular point, we will be using a more accurate line model, where the total charge of the tape will be evenly distributed over its entire length. Some of the physical principles that we will be working with are the idea that like charges repel and opposite charges attract, with a force equal in magnitude to each other. The second is this equation, called Coulomb's law, in which we will use to calculate the actual numerical value of the charge given in the SI unit coulombs. And finally, we will be using the fundamental constant, which is given as 1 over 4 pi epsilon naught and is equal to our value 9 times 10 to the 9 Newton meters squared over Coulomb squared. The first step in our procedure for the lab is the creation of the charged U-tape. First, we place one U-tape on top of a stack of books so that there is slack. Then, we record the length of tape B in order to later determine the mass. Then we grab another U-tape and hold it in our hands. We then move the A tape towards the B tape until the B tape begins to float. Once the system is at equilibrium, we record the distance D, which is the distance between the two floating tapes. The assumptions that we have to make for this lab are as follows. First, we must treat the tapes as a line of point charges. Then, we must assume that each tape holds the same amount of total charge distributed evenly along its length. The tape's mass is proportional to its length, 1 gram per meter, which we're going to use in order to determine the mass of our tape. And finally, the last assumption is that air resistance is negligible. The values that we recorded for this lab are first the length of the tape, which is 24 centimeters for both pieces, the tape width, which is 2 centimeters for both pieces, and the distance D between the tapes A and B in our experiment, which in this case is 3.5 centimeters. Finally, using these, we calculated the mass of the tape to be 2.4 e to the negative 4 kilograms. Here are some more of the calculations that we did. The first is determining the force of gravity, in which we used the mass value that we found earlier. And the second is setting the force of gravity equal to the electric force in order to find the total charge on the tape. Using our computational model, we can now calculate the electric field of each point charge on the upper tape due to each point charge on the lower tape. We then calculate the total electric force on the tape using this equation. And finally, we can compare the total electric force estimated by our computational model and the gravitational force to make sure that they are equal. Here's some of our code that we use in order to calculate certain values. The first one is the function that we use to calculate the electric field. The second one is the function that we use to set up the visual model of the tapes, which creates spheres and lines in order to see the line of point charges. Finally, there's a nested for loop to calculate each electric field due to each point on the bottom tape onto the top tape. And then we use the concept of superposition to add it up and find the net electric field from the bottom to the top tape. Here we have the output from our code. The top tape is represented by red dots, and the bottom tape is represented by blue dots. These dots are to show that we're assuming that each tape is made up of individual point charges which make up a line. The green arrows on top are meant to show the individual electric fields on each point charge from the bottom tape onto the top tape. The white arrow on top represents the net force that these individual electric fields cause. The yellow arrow represents the force of gravity onto the red tape, onto the top tape. And on the bottom we have the output of the magnitude of electric force that we calculated and the magnitude of the gravitational force. We can see that they're not exactly the same, and this is due to human error and estimates going wrong in our experiment. Now finally we have some questions. First one is, well, what if you had modeled each of your tapes as a single point charge like in the previous lab? And the second is, if they differ, why do they differ? Which value is more likely to be closer to the real-life value, and why? If we had modeled our tapes as a single point charge, we would have gotten the same estimate that we did in Lab 1. The reason that Lab 2's estimate is almost twice as small is because using the line charge model, the individual point charges towards the end of the tape are going to have less of an effect in the y direction than the point charges in the middle of the tape, resulting in an overall lower charge.